Welcome back, and also welcome to this new lecture series that is going to be started by Professor Johanna Erdmenger. And this will be on holography and its applications to understanding QCD. So Professor Erdmenger is very well known for her work on top-down constructions of holographic models for QCD using string theory, and she has done many remarkable contributions in this subject. One of the most important things to mention is she was one of the first groups to calculate that string theory predicts new kind of transport coefficients in hydrodynamics, which is a consequence of quantum anomalies. And her calculations revealed these new transport coefficients which Landau thought should not exist. And then she went on to make many important contributions, especially using top-down approaches to even study condensed matter problems like the Kondo effect. And there she is very well known for her work. And recently she has also written a wonderful book which my students and probably almost all graduate students presently are using to learn about holography. And this book is published by the Cambridge University Press, and it's co-authored with Martin Ammon. So it's a great pleasure to have Johanna, and I'm sure you will enjoy her lectures. And as usual, feel free to ask questions and discuss with her after lectures.
I'm going to give 5 lectures on the introducing holographic QCD. And so this gives me quite a lot of time, so I can really start from the beginning and give you lots of details also about the AdS CFT correspondence itself. Okay, so today I have a slides talk where I give you some overview and motivation about what I'm going to do. And I think tomorrow I start with one Blackboard talk on more details about AdS CFT. But today, for this overview, I think it's very good to have slides. Okay, so let me give you a brief outline of the 5 lectures which I'm going to give to you. So you see there's 6 topics, so there will be more than one topic per lecture. And so that today I'm going to start with AdS CFT, and so what it actually is, and then how you can actually apply it to strongly coupled gauge theories. So the topics I'm going to cover, I will say a little bit about transport properties as relevant for the Quark-Gluon Plasma, but there will be more specialized talks on this, so there I'll be somewhat brief. But then, on the other hand, I'll be quite explicit on how to model chiral symmetry breaking in gauge gravity duality models, and also on how to calculate properties of mesons. And so one very nice feature I'm going to show to you that you can compare these holographic computations to lattice gauge theory results. If I have time towards the end, I would like to show you a little bit about some new developments which are ongoing to apply this to deep inelastic scattering. And so then there's this very important current topic of the entanglement entropy, and I hope to say a little bit about this also. Okay, so today I'm going to be pretty general and give you an idea what this is all about. So it's called the big picture. So I was very proud because at lunch, I think Ayan said to me, well, today you should give them the big picture. And then I was already smiling because I knew that on my first slide it said the big picture. So obviously I was doing the right thing. Okay, so what's the big picture? Okay, so the very big picture is that I would kind of advertise this topic by saying that currently there's well, of course there are many challenges in theoretical physics, but there are 2 very important ones which I would like to mention in this context. And so the challenge number 1, which we've been working on for, I would say, for the last 80 years, and lots of interesting concepts have been developed, but the question itself has not really been solved yet, is to find a unified theory of all known interactions. So on one hand side, the theories of the standard model, so electromagnetism, the weak and strong forces. So as you know, these can be formulated as quantum theories. And then on the other hand, the fourth force is gravity, but as you all know, gravity can't be quantized the same way as these other 3. And so there's issues of non-renormalizability. And so one of the challenges I would like to put forward is the challenge of actually quantizing gravity and formulating a theory of all known, quantum theory of a unified quantum theory of all known interactions. Okay, so this challenge has been around for 80 years, and many interesting ideas have already followed, but I don't think it's a solved challenge. Okay, so challenge number 2 is a quite different challenge, and it's much more applied in the sense that if we do quantum field theory, then there are very elaborate techniques when we are in the perturbative regime. So when the couplings are small, then perturbation theory is extremely powerful and extremely precise, and many beautiful results have been obtained. And then the question about strongly coupled systems is still an unsolved problem. And of course, there are methods like lattice gauge theory or other approaches to strongly coupled systems, but they all have some drawbacks. Like, for instance, there's the sign problem, which arises if you have to go to a Euclidean scenario for your lattice, for instance, which makes it hard to describe, for instance, a chemical potential or transport processes. And so any idea which goes beyond perturbation theory would certainly be very welcome. So on one hand side, this is of course relevant for QCD at low energies, which is certainly where the beta function is negative. But then there's many other areas of physics. So here this is a high TC superconductor where similar problems arise. And this is, so Ayan mentioned that there's even applications of this in condensed matter physics, because in any area of physics, there are not so many methods for describing strongly coupled systems. So if we can come up with a new idea, this is extremely welcome. Okay, so then the challenge is to go beyond perturbation theory in describing observables and processes in systems with a given interaction. Okay, so as I said, the prototype example is already non-abelian gauge theory, so Young-Mills theory, and so which has a negative beta function. So I'm sure you have seen this before, and when you go to low energies, then instead of looking at quarks and gluons, you have to look at mesons and baryons, and this is still an unsolved problem, how this theory goes from the one picture to the other one. In particular, there's very famous Clay Millennium Prizes, and one of them is to actually solve this theory, solve this theory in the strong coupling regime. So you can win $1 million, so it's certainly an open question still. Okay, so let me briefly explain what strong coupling means in a very physical picture. So weak coupling means that, I mean, in a classical theory, you would have some blue particles, say, and then if this red, you want to consider the physics of this red particle, and the coupling is very small, then you can just individually look at this particle interacting with all the others if you want. And okay, so of course this particle picture is very simplistic, but in perturbation theory you still have this quasi-particle picture, so where the number of states in the interacting theory is still exactly the number of states in the free theory, and then then you're in the perturbative regime, and then things are very much under control. Now, if the coupling is bigger than 1, then, okay, so this means that all the particles, they form a kind of collective system. So if you want to describe the physics of this particle, you have to describe the physics of all the other particles at the same time. And that's what's making life hard, and so that's why it's not so easy to present a simple method to solve this problem. And so, in particular, the application of perturbation theory is not possible. Okay, so now the upshot of this talk is that, so there is a recent development, okay, so I would say recent, okay, it started in 1997, so maybe for me this is still recent, maybe for you it's not quite as recent, but okay, certainly it's much younger than anything I said before. So the new development leading to AdS CFT engaged gravity duality is, so I presented to you these 2 challenges, and actually the upshot of this lecture will be that these 2 challenges are related to each other. Okay, so if you have this challenge number one of finding a unified theory of fundamental interaction, and challenge number two, which is the description of strongly coupled systems, then we will discover that these two challenges are much more closely related than we thought. So that's very interesting. So we didn't solve any of the two challenges, but we showed that they are related. So which already provides quite a lot of information. Okay, and so this relation comes through this concept of gauge gravity duality. That's what I'm going to explain in these lectures. So the AdS CFT correspondence is the most famous example of a gauge gravity duality because it's an example which has a huge amount of symmetry, and then that makes life a lot simpler, and so things are very, very much under control. So I also start by explaining the AdS CFT correspondence, but later when we think of QCD, we will look at more general examples of such a gauge gravity duality. Okay, so let me begin very, very simply. So what is actually a duality? Well, okay, this word duality has many, many meanings, both in physics and in mathematics. So here I'm going to use a very physical working definition of the word duality. So imagine you have some physical system which you can study, I don't know, in your theory or in your lab. And then you discover that you actually have two different theories. So by theory, I mean something given by an action or a Hamiltonian, written in a particular set of degrees of freedom. And then you discover that you have two different theories written at different degrees of freedom, which actually describe the same physical system, which you consider. And so, I mean, you might think that's pretty rare, but actually there are quite a few examples. You know, there's this duality between the Thirring model and the Sine-Gordon model, for instance. And so there's a number of, and in string theory, there are lots of these dualities. So it's not so rare in physics. However, there's something very special about the duality I'm going to talk about in a minute. So the first statement is, once you have the situation that you have two different theories with different degrees of freedom describing the same physical system, then you say that these two theories are related by a duality. So that's my working definition of this word. And so the special thing, so what makes gauge gravity duality special is that that a theory without gravity is dual to a gravity theory. So you have a strongly coupled quantum field theory, which is dual in the sense of this definition to a gravity theory. Okay, so before I go any further, I should say, so gauge gravity duality is still a conjecture. Okay, so there's no mathematical proof of this duality, and it's certainly not as simple as a duality relating to quantum field theories. And so it's a conjecture which follows from a particular low energy limit of string theory. And I'm going to show you a little bit about this limit because this will be essential for actually describing quarks and gluons later on. Also, it has this property which I advertised, so it maps a quantum field theory at strong coupling to a theory of gravitation at weak coupling. And now the next important thing which we also will study is that it has this property of holography, which means, for instance, that if you have a quantum field theory in 3+1 dimensions or 4 dimensions, then essentially it will be mapped to a gravitational theory in 5 dimensions, so in 1 dimension higher, but there will be also more internal dimensions which will show up later, which I'm going to explain. But you can imagine that your quantum field theory is defined at the boundary of some curved space, which is described by this gravitational theory. Okay, so the best understood example of this gauge gravity duality is the AdS CFT correspondence, so where AdS stands for anti-de Sitter space and CFT stands for conformal field theory. And so first, before I explain what the relation between these two things is, so let me first explain what an anti-de Sitter space and what a conformal field theory is. So tomorrow I will do this with many more formulae, but today I would just like to show some pictures. So an anti-de Sitter space is a hyperbolic space. So it's a space of constant negative curvature and it has a boundary. So both of these properties are very essential for formulating the AdS CFT correspondence. So, okay, there's different ways of writing the metric. So in the so-called Poincaré patch, which also I'm going to explain tomorrow, you can write the metric of the space. So this is your usual Minkowski metric. And then you just add one dimension called R here. And then you have the so-called warp factor here at the front. So because the exponent has to be dimensionless, this introduces a scale L. And this L is called the anti-de Sitter radius. So you can imagine this anti-de Sitter space as a kind of half cylinder. And time, so the time points in this direction. So this is a cut through the space with a projection at a constant moment in time. So it's a nice picture by Escher. And the meaning of this picture is that these angels and devils, they all have the same area. So, so just because the space is negatively curved, the areas in the middle, they look much bigger than the ones at the boundary. And that's exactly the other way around. And if you had, say, a sphere which is positively curved and you do a projection onto a plane, my favorite example is always that of remember, the Mercator projection. So this is, if you want to make a map of the world, so the world is a sphere. So if you map it to a piece of paper, this piece of paper, the simplest you can do is a cylinder. If you do that, then the continents which are the two poles, they appear much bigger than the ones which are closer to the equator. And here, because the space is negatively curved, it's just exactly the opposite. Okay, so the things which are in the middle, they look so much bigger than the things which are at the ends. Okay, so that shows you the difference between the two curvatures. Okay, so we have this hyperbolic space, and it has a boundary. Okay, so here, this is drawn here in the slightly more mathematical terms. And so we have this hyperbolic space of constant negative curvature. And we can, if we take Euclidean signature, we can consider a D plus one dimensional anti-de Sitter space to be embedded into a flat D plus two dimensional Minkowski space by this equation here. Okay, so essentially it's like a sphere of radius L squared, except one sign here is different than the other signs. Okay, so if you had a constant curvature on this side, and if you had a positive curvature, the signs would all be the same. So the fact that one sign is different means you have a hyperbola. And so, essentially you consider, this is now an example in low dimensions. So this blue hyperbola is your anti-de Sitter space, and essentially if you carry this out all the way to infinity, then the circle at infinity will be your boundary. Okay. Now, given this equation, you can immediately write the group of the symmetries of the isometries of the space, and it's given by this group SOD plus 1, 1. So if you did this in Lorentzian signature, it would be SOD, 2. And as I said, on the so-called Poincare patch, which is a local coordinate system which covers half of the space, you can write the metric as follows. So here, this Z is defined in terms of, I think, e to the minus R over L, and then you get a coordinate system which looks like this. Okay, and so here in this case, the boundary is when this Z goes to 0. And then that looks somewhat divergent, but it's just an artificial coordinate singularity. It's not a curvature singularity, so the curvature is just constant everywhere. Yeah. Okay, so on the other side of the correspondence, in addition to this anti-de Sitter space, we have the conformal field theory. Now, what is a conformal field theory? So that's it's a particular kind of quantum field theory. And it's a quantum field theory in which the fields transform covariantly under conformal transformations. Okay, so conformal transformations are conformal symmetry coordinate transformations, and they are defined by this equation here. So, so if you get a new line element from an old one, you just get it by multiplying by some particular function. So imagine you had a general coordinate transformation, then you would have two matrices here acting on these indices. But here, this coordinate transformation takes a special form where instead of these matrices, you multiply by a scalar function, which happens to be called omega squared for some reason. And if this is the transformation, then locally angles are preserved in your theory. Okay, so as you can see, this is a pretty big symmetry, and certainly not every quantum field theory in physics is conformally invariant, certainly not. So you can see it's a kind of generalized scale transformation. So scale invariance is a necessary condition for conformal symmetry, and so this means you can only have this renormalization group fixed points. So a theory which is as a renormalization group fixed point, then you can imagine to have conformal symmetry. I think in 2 dimensions you can probably prove that any scale invariant theory is also conformally invariant. In higher dimensions, it's a bit more complicated, but okay, so, but if you have this huge symmetry, it means that your theory is much more simple than any general quantum field theory. And in particular, the correlation functions in the theory are determined up to a small number of parameters, okay? So essentially, you can imagine that you just have a few forms, independent forms, which contribute to your correlation functions. For if you have scalar fields and with a 2 or 3 point function of scalar fields, then actually there's just a 1 general coefficient, and everything else is dictated by the symmetry. So a long time ago, when I wrote my PhD thesis, I actually studied the structure of correlation functions in these conformal field theories in 4 dimensions, and especially the 3-point function of the energy momentum tensor, and so which has 3 independent components. So that's just dictated by the symmetry. And so once you know your theory is conformal, many things are fixed before you even start to do any calculations. Okay, so if you wonder what I did for my PhD, this was the study of this correlation function, and so just as a kind of a side remark, so I finished my PhD in November 1996, and then I was almost the only person in the world interested in conformal correlation functions in 4 dimensions, but just 1 year later, there was the AdS CFT correspondence, and suddenly everybody started my PhD thesis. So these are the things you just cannot predict. And so I was doing something really exotic and off the beaten path, and only a few experts were interested. And 1 year later, suddenly everybody read my PhD thesis. So yeah, as I said, these are really things you can't plan in your life. And so this means if you enjoy something, you should just keep doing, and maybe everybody will be forced to read your PhD thesis. Good. So now, so far, I was talking about really general conformal field theories. But in the AdS CFT correspondence, if we stick to the example of 3 + 1 dimensions, one considers a particular conformal field theory. And okay, there are not so many conformal field theories in 4 dimensions, and certainly this is the best understood example. And so the name of the theory is NX4 SUN super Young-Mills theory. So note there's 2 different ends. There's a curly N and there's a straight N. Okay, so they have a different meaning. This is related to the supersymmetry of the theory, and N is the rank of the gauge group. Okay, and so this theory has the property that it's conformally invariant even when it's quantized. Okay, so we can show that the beta function of the theory vanishes to all orders in perturbation theory, and also non-perturbative corrections such as instantons actually vanish. So in one sense, it's a very normal quantum field theory because you can just write a Lagrangian and it's more renormalizable and everything. But on the other hand, it's very special because it has this property that its beta function vanishes explicitly for all values of the coupling, so that's rather special. Okay, and this theory has a particular global, so this is a gauge symmetry, okay? But this theory has also a global symmetry, and so it has an SO4,2 symmetry, so that's the conformal symmetry in Lorentzian signature. So the symmetry group of these transformations in 4 dimensions is SO4,2. And due to this large amount of supersymmetry, it also has a global so-called SU4 symmetry group. So that's the so-called R symmetry of this theory. So you can see this theory has a huge amount of symmetries. Sorry. Okay, so now the AdS-CFT correspondence makes the statement that, okay, so this is my cartoon of an anti-de Sitter space. It's not a very good cartoon because this curved space looks kind of finite, but it's not. Okay, so this extra dimension is non-compact. It goes all the way to infinity. But just imagine this as a kind of toy model of a curved space which has a boundary, and the boundary is supposed to be this here. Now you can actually show that an anti-de Sitter space has a boundary which is a Minkowski space. And so if you have a 5-dimensional anti-de Sitter space, you can put a 3+1 dimensional Minkowski space at it. Its boundary is a 3+1 dimensional Minkowski space, essentially. Now, so what AdS-CFT states is that you actually have a dictionary, so a one-to-one map, which gauge invariant field theory operators in this theory at the boundary are mapped to classical fields in the gravity theory. So this means, for instance, if you take 2 insertions of these operators here and there, then you can calculate the correlation functions quantum mechanically by studying Feynman diagrams. Okay, so this is a very rough abbreviation for Feynman diagrams. You can calculate in a quantum field theory the correlation function of this theory. And now the AdS-CFT correspondence states that you can calculate the same correlation function by looking at classical propagation in this extra dimensions. Okay, and so it's classical, but the propagators are more complicated because the space is curved. And so then essentially you can map gauge invariant field theory operators to classical fields in the gravity theory. And this one-to-one map works precisely because the symmetry properties of these 2 objects coincide. So this is the first kind of more quantitative statement which I'm going to make. So on the field theory side, we have a conformal field theory in 3+1 dimensions. So I just told you, so it has, let me go back. It has this symmetry because it's conformally invariant, the beta function vanishes, and it has that symmetry because it's supersymmetric. And before, I was discussing the symmetries of anti-de Sitter spaces. Okay, and I told you that in Euclidean signature, the symmetry of the isometries is SOD plus 1, 1. If you go to Lorentzian signature, it will be SOD, 2. Now, if d is equal to 4, this also is SO4, 2. Okay, so the isometries of this anti-de Sitter space in 5 dimensions have the same symmetry as the fields in the 3+1 dimensional quantum field theory. Okay. So that's already super important that the symmetries match. And then I will also, in a few slides, show you that this SU4 symmetry is also realized geometrically in the gravity picture. And so that's one, okay, so as I told you, no proof of this relation that we can say the quantum field theory here is equivalent to the gravity theory there. But there's essentially 2 reasons which, as physicists, since we are physicists and not mathematicians, we are led to believe that this must be true, because the symmetries are the same on the 2 sides, and they're very, very strong symmetries. And also, as I'll discuss later, the number of degrees of freedom is the same in the 2 theories. So if you have 2 physical theories with exactly the same number of degrees of freedom and exactly the same huge symmetry, then there's almost no choice that then these 2 theories somehow have to be the same. Okay? Okay, that's not a mathematically sound argument, but certainly is a very good physical motivation why this correspondence holds, at least for the AdS-CFT case. And there's actually many very non-trivial tests of this conjecture, in particular by actually really calculating these correlation functions and subject to some normalization. So there's always a scale which you need to fix. You can do quantum computations here and classical computations here, which look completely different, and nevertheless you get exactly the same result. So two totally different calculations give you exactly the same result. So that's super impressive. And certainly during this week I will show you some examples. Okay. So the thing which is still missing now in my argument is that I have to explain where this SU4 symmetry, which is present in the quantum field theory, appears in the gravity theory. And the statement is, as I will also explain in more details, that since AdS CFT comes from string theory originally, maybe you have heard that for some anomaly cancellation reasons, supersymmetric string theory is consistent in 10 dimensions. Okay? The reason why string theory is like 10 dimensions is because then there's some cancellation of some unwanted anomalies. And this means we don't just have a 5-dimensional anti-de Sitter space, but we have to have a 10-dimensional space. And this 10-dimensional space will consist of a product of both this 5-dimensional anti-de Sitter space and a 5-dimensional sphere. Okay? So that's the simplest you think you can do to fill 5 dimensions, is just to have a sphere. And if you have that, then actually you now explicitly see that the symmetries of the field theory and the geometry coincide, because AdS5 has, again, this SO4,2, the same as the conformal symmetry, but now a 5-dimensional sphere has an SO6 symmetry. And SO6 is isomorphic to SU4. So SU4 and SO6 are the same. They're isomorphic, and so essentially this is your geometric realization of this SU4 group. Okay, so this already brings me to a very important point, which will also show up when I discuss applications to QCD. That, I mean, it's very important to also consider this internal manifold. I mean, we have AdS and the boundary, so here our quantum field theory is defined here as the boundary. But to really have the full duality, we need this 10-dimensional space. And it's actually the symmetries of this internal manifold which determines the field content of this dual quantum field theory here. Okay? And so these extra 5 dimensions, they're also very, very important. So if we just have an AdS space, that just tells us we have a conformal field theory. But if you want to know which conformal field theory, you have to introduce this internal manifold, because the symmetries will determine the field content of the conformal field theory. Okay, that was already quite a lot. I will give many more details tomorrow, but are there any urgent questions about this? So you should tell me if am I too slow or am I too fast, or I mean, I can. Well, I guess I haven't given you enough details to answer this question, but so let me say that tomorrow I will write equations on the blackboard, and then it will be much more definite. I mean, this is really meant to be an overview about things. I mean, can you just give me some feedback? Have you never seen this before, or don't be afraid. I mean, if you say yes, then this is perfect. I know what to do. Or are you already all experts in it? Yeah? Yeah, sure.
If you say that the counting out degrees of freedom and symmetry makes it obvious for physicists that this conjecture has to be true, why don't we have a proof?
Okay. Can you hang on for 10? I'm going to explain why there's no proof in the next 10 minutes of my talk. I will come to this right now. It's the reason is we have to understand where this conjecture comes from, and I will tell you what would be necessary to actually prove it. And then you will see that we cannot do it at present. Okay, but I think somebody else at the end, you didn't want to say anything? Oh, okay, good. Okay, but this is a very good question. I will come to this now, actually. Okay, just one side remark. Okay, the upshot of these lectures, remember what I said at the very beginning about relating these two challenges of theoretical physics, and that will be the upshot of my lectures. I want to generalize AdS. So AdS CFT is very beautiful and very symmetric, but it's so symmetric that it's not really describing a particular system in nature. I mean, that's always kind of a problem when you do theoretical physics. There's a conservation of difficulty. I mean, either things are super beautiful, very, very symmetric, and you can do lots of calculations, or they describe the real world, but it's very rare that these two things coincide. And this is, of course, the same problem arises also here. So we can't directly apply AdS-CFT to point of view theories of experimental relevance, but I will show you in these lectures how, or at least we can make some important steps towards this goal. And so, as you will see in the next lectures in this week, the prototype example for applying this is low energy QCD, because it's also a strongly coupled gauge theory as the one appearing in the AdS-CFT correspondence. Of course, QCD is very different from this N=4 supersymmetric quantum field theory, which I just introduced. So it's an SU3 gauge theory, and it has gluons and quarks. So what is useful is it's strongly it's strongly coupled, which makes it not very accessible to perturbation theory at low energies. And the bound states are mesons and baryons, and it has a negative beta function rather than a vanishing beta function. Okay. So to actually get closer to this, we will have to add quite a lot to the original AdS-CFT correspondence. But let me first explain the original AdS-CFT correspondence and come to this question why we can't prove it. And then once we understood that, we see a few knobs which we can turn to get closer to this. So we can certainly get a negative beta function. The only thing which we can't, and we can study mesons, partially also baryons, but certainly one thing we can't do is to get to this SU3 gauge theory. So I told you that our original theory was an SUN theory, and n goes to infinity. And of course, that's also a valid approximation to QCD, which is due to Toft already from 1974, but it's not the true story, okay? And this is the only thing which we won't be able to get to very easily. And that's actually tied to this question why we can't prove the AdS-CFT correspondence. So we have to live with the fact that this will be n or not 3, and n will be very big, okay? But okay, I mean, it's a start. Okay, so during this week, I'm going to show you that we can generalize the original AdS-CFT correspondence. First of all, we can relax some of these huge symmetry requirements in a controlled way. We can describe renormalization group flows, so include a finite beta function. We can also go to finite temperature and finite density as relevant to the Quark-Gluon Plasma. Then something I'm really going to discuss in some detail is that we can add more degrees of freedom, for instance, quarks. So the original theory only has gluons if you want, but we also want to study quarks, especially if we want to consider mesons. And as I already said, I mean, the thing which we can't really change is that this large n limit continues to apply. So we can't really have an SU3 gauge theory in this context. Okay. Now, to answer this question, why is it not possible to prove the correspondence, I have to tell you a little bit about string theory in 5 minutes. Okay. Okay. So first of all, I should say there's two different approaches to the AdS-CFT correspondence, which are called the top-down and the bottom-up approach. Mostly in this talk, I will focus on the top-down, but there are many, many interesting things which can also be done in the bottom-up approach. So top-down means that we start with string theory in 10 dimensions, and I already explained why 10, because string theory is consistent in 10 dimensions. And also this internal manifold, so this circle, this sphere which I showed to you, ensures that the Lagrangian of the dual field theory is known, and we have only very few parameters in the problem. Okay, so that's all very nice. However, this is generally quite complicated because, I mean, string theory is generally complicated. Okay, so then the bottom-up approach is a bit different, and there people just say, okay, we just deform the AdS space to get a flow in a conformal field theory. But, you know, this 10-dimensional space is too complicated. Let's just ignore it and just calculate in 5 dimensions, okay? Then, of course, things become much simpler. However, then only the global symmetries of the dual field theories are known, and we cannot write down the Lagrangian of the dual field theory anymore. Okay, so either things are complicated and complete, or they're simple, and so if you drop a few things to make it simpler, then of course you lose some information. I mean, it's obvious. And depending on what you want to do, both of these approaches, they are very valid. But we have to keep in mind that, you know, there's two different things we can do. So then you may ask, why is this bottom approach useful at all if I don't know what the Lagrangian is? Well, I mean, sometimes the physics doesn't depend on the microscopic degrees of freedom, and you can just work with some universal behavior, and this bottom-up approach is very, very effective as identifying universal behavior in strongly coupled field theories, and this can be extremely far-reaching and very useful, and this I'm also going to show you examples for that. Okay, so let's first begin with this top-down approach. By the way, my watch is still to European time, and especially with this half-hour difference, this is very confusing. So can somebody tell me what the time is? This is the time which has already elapsed. No, it counts backwards. I have still 41 minutes. Excellent. Okay, thanks. Good. Sorry. Good. I want to come to your question about why it is difficult to prove the correspondence. So everything I'm going to say now is in preparation of the answer to this question. Okay, so okay, so in this top-down approach, we use 10-dimensional supergravity actions obtained from string theory. So it's complicated, but it's well defined. To describe the dual degrees of freedom in the strongly coupled field theory. And so to explain this, I have to tell you just a very little about string theory. But okay, so this is my 4-slide introduction to string theory without any equations. Okay. Good. So the idea behind string theory is to find a quantum theory of gravity and to unify a unified description of all 4 interactions. So this is was developed in the context of this challenge 1, which I mentioned at the beginning. And so the question is, how do you quantize gravity? Well, you avoid this regularization or non-renormalizability issue by giving up locality at very short distances. And if your particles are no longer point-like, but they're extended, then there's a natural cutoff, which is the string length. And so the string length essentially is given by 1 over the Planck mass. So this is a super short length scale of 10 to the minus 35 meters. Okay, it's very small, but it's finite. So, and that essentially is at the heart of circumventing this problem that we can't quantize gravity because we have this natural cutoff in our theory. Now, for AdS CFT, there's a very important fact which is going about string theory, which will enter very decisively. And so in string theory, you can have either the so-called open strings or you can have closed strings. So open strings, this is an example of an open string. So there you consider a string like a string on a violin or guitar or piano, which is attached on the 2 endpoints with some boundary conditions. And then the string just vibrates between these 2 endpoints. And actually, if we take a low energy limit, then these open strings will lead to a description of gauge interactions. Now, why is that? I mean, just very, very naively, if you consider the lowest fluctuation mode of a string which is attached at the 2 ends, it will go up and down like this. And now, if you remember your course on classical electrodynamics, if something goes up and down like this is exactly a dipole moment in your antenna. Okay, so in a dipole moment, if you remember this multipole expansion, which certainly I learned about in my classical electrodynamics course. So then the first, so there's a monopole, then next term is a dipole. And the dipole is essentially a vector, p mu. So it's a spin 1 object, okay? It's an object with 1 index. And the other object with 1 index, which appears here, of course, will appear here, is the gauge field. Okay, so you can identify this dipole with your gauge field. So the lowest mode, the massless mode in the fluctuations of the open strings will be this dipole mode, and this will be a spin 1 object, so a gauge field. On the other hand, you can also have closed strings, so which don't have endpoints. And there it turns out that the massless mode is actually a quadrupole fluctuation. Okay, so something, so if you have your string, like the string, it goes like this, like that, like this, like that. Okay, this is this quadrupole, and a quadrupole moment has two indices, so it's more like a metric. A metric also has two indices. So the massless fluctuation associated with such a closed string, they will correspond to gravity. So these open strings, the lowest low energy modes of open strings naturally are gauge modes, and the lowest, the massless modes of closed strings are naturally gravitons. So, and later I will show you that we have a duality between gauge theories and gravity theories, which then, as you can already see, means we will have a duality between open and closed strings. Okay, so that's already at the origin of this correspondence. Okay, so in string theory, the higher oscillation modes then correspond to the particles of your theory. Okay, so as I already mentioned, if you now quantize a string theory, you discover that supersymmetric string theory is well defined in 9+1 dimensions, because you can consistently get rid of tachyons, and there's also the anomalies vanish. And supersymmetry means that you have a particular symmetry between bosons and fermions in your theory. Now, then, of course, the question arises if we start in 10 dimensions, and in the end we want to do QCD, so we have 6 dimensions, which are kind of superfluous, but they have a completely different meaning than the 3+1 dimensions of our real world. Okay, so what's the meaning of these extra dimensions? Well, in string theory, there's actually 2 possibilities what you can do. So many people work on this idea of compactification. So this you may have heard. So these 6 dimensions, they're wrapped on very, very tiny curves, and this gives very beautiful structures, these Calabi-Yau manifolds, and there's many possibilities of doing this, and this leads to this idea of the landscape and so on. Maybe these are just words which you have heard. But this is not what we are going to do. Okay? So we will consider a particular low energy limit of the so-called D-Branes. So D is the abbreviation of Dirichlet boundary condition. And this means we just put some particular subspace into our 10-dimensional space, which is then our real world in 3+1 dimensions. And these 6 perpendicular directions, they will essentially correspond to the fields of our theory. Okay? So they will have a slightly different meaning than a geometrical dimension. Okay, so what's a D-brane? Well, essentially a D-brane is a surface which is embedded into this 10-dimensional space. So, which you can see here, and then you can have open strings attached to it. So Dirichlet stands for Dirichlet boundary condition. So this means on the surface you can provide the boundary conditions for these strings. Okay, and now because we want to do QCD, in the end we want to be in 3+1 dimensions, so we will consider the so-called D3-branes. So 3 stands for 3 spatial dimensions, and then there's 1 time dimension also. So we consider these 3+1 dimensional hypersurfaces on which we provide endpoints, boundary condition for the endpoints of the open strings. So the open strings may end on the D-branes, and their fluctuation will give the dynamics. Okay, so in this way, we can construct our gauge theory. So the gauge theory will be on this 3+1 dimensional hypersurface, and the gauge fields are the lowest energy fluctuation modes of these strings. Okay, so, and if, in particular, if we take a very low energy limit, so essentially we go so far away that we can't resolve the structure anymore, then the strings look point-like again, and then the open strings will just be given by dynamics of these open strings just corresponds to a Lagrangian for the gauge theory of freedom on gauge theory degrees of freedom on the brane. Okay, so that's kind of the picture number 1, the quantum field theory picture of branes, and so that's the kind of gauge theory side of things. Now, what's very interesting about the branes is that they have a second interpretation, and they have an interpretation in the context of gravity. because these branes, they can also be viewed simultaneously. So this is, remember when I introduced the concept of duality on the second slide, okay? I told you what's my definition of duality. Well, you have one physical system, and there's two different theories which describe the same physical system. And now this is precisely a realization of this. So our physical system will be these branes, and then there will be an open string theory and a closed string theory, both describing these branes. And then they will be dual to each other. So the second interpretation of the D-Branes is that they are so-called solitonic solutions of 10-dimensional supergravity. So solitonic means that they're kind of wave packets which don't dissolve. And in particular, in this context, these D-Branes, they have a mass. They also have a charge, but they also have a mass. So they're very, very heavy. And so now if you put a very, very heavy object into a flat space, then this curved space will be curved. Again, when I give these kind of talks, I have always this very nice example. Imagine you meet with two friends, and your two friends, they both take a bed sheet or a tablecloth, and so each of them holds one end of it, and that's your flat space. And then you take a pumpkin and put it in the middle of this tablecloth, and then obviously the tablecloth is going to it will be curved, okay? And okay, that's a two-dimensional example, but it's exactly what's going to happen here. If you put this very heavy 3 + 1 dimensional object into your 10-dimensional space, then the 10-dimensional space will be curved. And that's where we get our anti-de Sitter space later. Okay. Okay, and because this is our gravity, as I told you before, with this quadrupole argument, so the elementary excitations will be closed strings. Okay, so now the AdS CFT correspondence is a map which maps a 4-dimensional quantum field theory to a 5 + 5 dimensional gravity theory, so it's in 10 dimensions. So 5 for the anti-de Sitter and 5 for this internal sphere. And this map arises from identifying the two different interpretations of the D-Branes, which I just showed to you. Okay, and now if we take these three branes, then this open string theory will be precisely this NX24 super young Mills theory, which I was talking about before. And according to my definition of duality, which I gave at the very beginning, this will be dual to a string theory on the space AdS 5 times S5. So this is all a motivation for the AdS CFT correspondence. Okay, so everything I saw on the last 4 slides is now summarized on this slide. Okay, so here's the string theory of AdS CFT. So we consider these three branes in the flat 10-dimensional space, and we consider many of them, n of them. Okay, so n of them are put on top of each other, and they actually charge. So then instead of just having a U1 gauge theory, we have an SUN gauge theory. And now I told you there's these two dual interpretations of these D-Branes. So either they serve as endpoints for boundary conditions for the open strings, or they're very heavy objects which curve the space around them. But since these two pictures are dual to each other within string theory, then essentially we may identify these two pictures. So here we have open string excitation, here we have closed. Now, and so this is the picture which Maldacena proposed in 1997, and so now the second ingredient in this duality is now a very ingenious low energy limit which is taken. Okay? Because the same limit which takes this string theory picture to a supersymmetric SUN gauge theory in 4 dimensions with point-like particles and the rank of the gauge going to infinity, so this means we take very many of these D-Branes. The same limit in this picture provides you supergravity, again, so a theory of point-like particles, but with gravity on the space AdS 5 times S5. So, and if these two theories are dual to each other, then those two theories should also be dual to each other. So that's the kind of motivation, the string theory motivation for the correspondence. Okay, so this can be summarized in this simpler picture, and in this picture now also allows me to answer this question, why can't we prove the AdS CFT correspondence? So So the idea is that first, there's a conjecture duality between an SUN quantum gauge theory for all values of n and for all values of the gauge coupling. And the conjecture is that according to the rules of string theory, this is dual to a particular string theory, which is the theory of quantum gravity. Sometimes when I give these kinds of talks, people also ask me, how can you map something classical to something quantum? Well, I mean, that only happens in this limit, which I'm explaining. At the original level, this is actually a duality between two quantum theories. Okay. So this is a very beautiful conjecture. The problem is that it involves string theory on the space AdS 5 times S5. And in fact, nobody knows how to quantize strings in a curved space background. People only know how to quantize strings in flat space. So we can write down this theory, but it's not possible at present day to actually do calculations in this. And that's already the one part of the answer why can't we prove the duality. Now, there are two particular limits which are now taken here. And essentially in the field theory, this amounts to a saddle point approximation. So one limit is that we take n to infinity. And as I will show you tomorrow in more detail, n is actually inversely proportional to the coupling of this quantum string theory. So GS, the string coupling, is proportional to 1 over n. So since I can't work in this quantum gravity theory, I have to take GS to 0. And this immediately means I have to take n to be infinite. Okay, so that's why we can't get away from this large n limit. The second thing is that in doing the saddle point approximation, I take the so-called Tuft coupling, which is a variant essentially of the gauge theory coupling for a large n theory. I take this to be large. So here we have our strongly coupled large n gauge theory. And actually taking this Tuft coupling to be large here on this side means to take the strings to be point-like. So I go to point-like objects here on this side. Okay, and then if I have this duality at this level, I should also have the duality of this at this level, and here we can actually do calculations because, okay, so this theory, it's a large n theory and it's strongly coupled, so this is something we would like to study, but normally it's very hard to study. But now we can use this duality to map it to something which is just classical gravity. So essentially calculations are simple because I just have to write my action, derive the Lagrange equations and solve them. Okay, so the standard things you do in a classical field theory. Now I can answer the question why it is hard to prove this correspondence, because a full proof wouldn't just be a proof at this level, it would be a proof at that level. But to be actually able to prove it at this level, I would first have to define exactly what I mean by the top right-hand corner of this diagram, but unfortunately it's not defined yet. So if I can't really say what this is, then of course I can't prove anything. So there's a very good physics motivation, but from a kind of more mathematical perspective. I mean, essentially, to really prove it, we have to have a better understanding of what quantum gravity is, and we don't. So, I mean, this duality, which I'm going to essentially apply to QCD, we will have to remember that I'm going to talk about this level. And so where we map our strongly coupled gauge theory to a classical gravity theory, but we should keep in mind that we have all the structure behind it, and which gives us, on one hand, some certainty that what we're doing makes sense, but on the other hand, it also reminds us that it's a conjecture, because we can't really define this top right-hand corner. Well, okay, so, I mean, it's a philosophical question what the word...
No, I didn't mean that way. I meant in the sense that if I can't write down a path integral or partition function or whatever you might want to call, and you don't know how to define, then when you actually find a way to define, you'll find that it is actually some null kind of a thing, and then the right-hand corner collapses.
Okay, well, okay. It's a very good question, but I think I have a very good answer. So First of all, I mean, I gave you only a very sketchy outline of all these string theory background. So, I mean, these dualities between open and closed string, this is something very extremely well established in string theory. So, I mean, there's some feeling that, I mean, that this should make sense. And of course, these in this picture, this is also what your question points to. These objects this site is actually a non-perturbative object. So, as I'm saying, non-perturbative objects are very hard to describe. So there's two answers to your question. The first of all is that the machinery of string theory provides many examples of dualities between open and closed strings, which are extremely well defined. The only problem with this one is that the gravity side is on this curved space. And but I would think that from a physics perspective, there's enough evidence that this is an object where, although you cannot write down a partition function, you have sufficient evidence to be talking about it. However, there's a second part to answering this question, which is, okay, here at this level, there's extremely many non-trivial tests. I mean, so after Maldacena's proposal for about 2 years, there were many papers, I mean, thousands of papers written of finding non-trivial examples where this duality actually works. And some of which I'm going to show to you. So, for instance, you can calculate the three-fold function of some particular operators in this quantum field theory, and you can also calculate it on the gravity side. And it's super complicated because you have to do a Kaluza-Klein reduction on this 5-dimensional sphere and so on. And it's two very, very non-trivial calculations, but in the end, they give exactly the same result, which I think is very surprising. Another argument, a very non-trivial test, is that you can actually calculate the so-called conformal anomalies in these two theories, both on the field theory and the gravity side, and again, it gives you exactly the same result. So there's a two-fold answer to your question. So first of all, even if you can't write a partition function, you have enough information about the theory to be able to formulate the duality at the level as I have presented to you. And the second is, once you take this limit, there's many, many very beautiful non-trivial examples which actually show that you get the same result into two non-trivial, very different calculations. So also in this application to QCD, there, of course, you cannot so directly compare because, I mean, in low energy, strongly coupled QCD, it's very hard to do explicit calculations. But the examples I'm going to show is some comparison with lattice gauge theory, where you calculate some meson masses in this large N gauge theory, and then also you calculate the same meson masses in the gravity theory, and you can compare to lattice gauge theory, and there's a surprising similarity of the result. And this is something I'm also going to show to you. So, okay, so although we don't have a proof, I think there's substantial evidence that this whole approach makes sense, and in particular, since there's so few possibilities of considering strongly coupled theories, it's always good to have one more and compare it with other approaches, and that's actually the point of this lecture. It's a good question, and I hope I gave some answer.
Can I have one more?
Mm-hmm. Sure.
Given this diagram, what should I really say are the underlying assumptions? One is the duality at the top.
Yes.
Then there is a capital N, not script, large assumption. And then there is a 't-Hooft coupling, which is presumably some lambda square N going to infinity also, is it?
Yeah, okay.
So no, my question therefore is really, in order to really say on so assuming just these three,
yeah,
the duality at the bottom follows. So this duality at the bottom has therefore corrections, so to say, from these three factors.
Okay, this is also something I wanted to explain with equations tomorrow, but I can do this right now. So let me copy the first two lines. So if we say SUN and gauge theory, and then here we have our string theory. Can you read this? Okay. On AdS5 times S5. Okay, so the first limit I'm going to take here is N going to infinity. Now, then, as you correctly say, I'm going to define the 't-Hooft coupling, which is essentially the Young-Mills coupling squared times N. But I also know that the Young-Mills coupling squared is actually equal to the coupling of the string theory times n. Okay. So then, obviously, just by elementary calculation, it means that GS is lambda divided by n. And this means now, since I want to take the limit GS to 0, because I can't write a partition function with this theory, then if GS goes to 0, and this lambda I want to make large and fixed, then obviously n has to go to infinity. So that's limit number 1. And then limit number 2 is that I take lambda to be large. Now, as I'm going to explain tomorrow, there's a very important relation which looks like this. So this is the radius of our anti-de Sitter space, this L which we had before. And this alpha prime is the inverse string tension, which is actually the length of the string squared. And then I think, I think this factor of 4 pi is actually defined into this. So this is again our lambda. So if I take lambda to be large and fixed, and this is also fixed, then this means that this has to go to 0. So essentially that means that LS is small. So this means in the units, essentially, I mean, this is a dimension for a quantity, but okay, we can normalize it with this L, for instance. So essentially, then if I take this coupling large such that I have a strongly coupled gauge theory, this means I get point-like particles. Okay, so the two limits are I take n to infinity, which means I get a classical string theory. The second limit is I take a strongly coupled quantum field theory, which means I get a gravity theory of point-like particles rather than a string theory. Okay, so if I take the length of the string to 0, then rather than a string theory, I have a gravity theory. Okay, so I will explain some more about this tomorrow. Any further questions? Okay, so let me show you one equation. So, I mean, at the moment, I was very general and I said, okay, this theory is equivalent to that theory. And we can be much more precise, and we can really have this one-to-one map between operators in the quantum field theory and particular fields in this gravity theory. And so this leads to this so-called field operator correspondence. So fields are in the gravity theory, operators are in the quantum field theory. And essentially this text here says exactly the same in this equation. Let me first read the text. So the generating functional for correlation functions of particular composite gauge invariant operators in the quantum field theory coincides with the classical tree diagram generating functional in supergravity. Okay, so if this is so these brackets mean the usual time-ordered vacuum expectation value of quantum field theory. And so I have some particular sources for these operators. Okay, so this means if I have a variable with respect to phi naught, I will get a correlation functions of insertions of these operators. Now, the key point is that the fields on the gravity side, they will be constrained by saying that their boundary value exactly coincides with the sources of these operators. So this means now if I take a functional variation with respect to these sources on both sides, this generates my correlation function, and here I get a tree diagram in the gravity theory. And so essentially you can think of the fact that these sources for your operators, which normally are classical functions which have no dynamical property, they now become dynamical objects in the dual theory, and they can propagate in this extra dimension. So that's how you want to view this. Okay, so the quantum fields theoretical sources for operators, they become dynamical fields which propagate in an extra dimension. Okay, and then due to this Kaluza-Klein reduction, so this expansion in spherical harmonics on the S5, there will actually be a relation between the operator dimension and the mass of these supergravity fields. Which looks like this. So L is the anti-de Sitter radius again. So if this gravity field has a particular mass, then the dimension of this dual operator will be related in this way, where D is the dimension of the boundary of the anti-de Sitter space. Okay, so the masses of the gravity fields determine the dimension of the operators. Okay, so if you didn't understand this, let me advertise the book, which Ayan already advertised for me, which was very kind of him. So in this book, everything is explained in great detail, much more than I can do here. But tomorrow I will try to put a few equations to...
Excuse me, I have a dumb question actually, because since you find the correspondence between our quantum field theory and the classical theory, what is this supergravity then? Is it just classical gravity or?
Yeah, it's a particular classical gravity theory. So this means it has a Ricci, so it has an Einstein-Hilbert term. Okay, this I will also, okay, let me write this down. Okay, essentially, if we start in 10 dimensions, then there's going to be a square root minus g, and then you have a Ricci scalar, and then you have this negative cosmological constant, and then there will be a number of complicated fields which you can write, especially so maybe in writing the language of forms. So this equation, okay, so in language of forms you can write that F is dA. Okay. So and so this is essentially just a one form. But then in higher dimensions you can also have an index, or you can have a form so-called Ramon form, which is called C4. And so this is an object which has 4 indices. And then you can define a more complicated gauge field, which is dC4. Okay, the same as this. And then there will be a number of these fields which provide some matter terms here in this action. So that's determined by the string theory construction. Okay, so there will be a Ricci term, there will be these higher order forms, and there's a negative cosmological constant. By the way, since you're asking this, how many of you, tomorrow I can start by giving you a 5-minute introduction to general relativity. Would that be useful, or are you all familiar? Do you all know what this R is? Yes, no, I mean, no, okay, good. So tomorrow morning I will spend the first 5 minutes explaining what this R is, okay? Okay, normally I think general relativity you should follow a one-term course, but I have an abbreviation which tells you the essential features in 5 minutes. Okay, I will start with that tomorrow. Or maybe I have 7 minutes, 7.5 minutes. Maybe I should do this right now. Okay, but then let me end the lecture today by explaining you general relativity in 5 minutes. Okay.
Johanna, should we leave the slide?
Well, maybe some people will ask, if you can you all read here? I can just do it here. I don't think I need so much space. Okay, so my idea of explaining what general relativity is, then we do this by comparison to electrodynamics. So, as you hopefully know, electrodynamics is a U1 gauge theory. Okay, so since you're all, I guess, from a QCD background, I think this should be a mega example. So this means if you have a U1 gauge theory, you have a covariant derivative. So this is all about electrodynamics. I'm just talking about electrodynamics. So, so if you have something like this, and this field phi transforms like that, then obviously this thing doesn't go, so it goes to e to the I lambda d mu phi plus I d mu lambda times e to the I lambda phi, if I'm not mistaken. Okay. So, this is not so nice because this is a kind of ugly piece, so you want to subtract this, so you define a new derivative d mu, which is d mu plus a mu. Okay. And a mu should go to minus I lambda, I d mu lambda. Then if you have that, then this means that if you do the transformation of d mu phi, then this will go to the I. Okay, because this transformation cancels this piece. Okay, I hope everyone is familiar with that. Okay, so then mathematically, this thing you can call this a connection. And then there's something called the field strength. And the field strength F mu is just d mu minus d mu a mu. In a U1 gauge theory, this object is gauge invariant. Okay, so I hope everybody has seen this before. And now, very quickly, so what is GR? This is the gauge theory of general coordinate transformations. Okay, so which means you do exactly the same story, except you have a different symmetry. You don't take U1, you take the general coordinate transformations. Now, and then instead of this a mu, you have a new connection, and this connection is called gamma mu mu, and this is called the Christoffel symbol. And then you can have a covariant derivative which involves this object instead of that. The only difference is the same as there, but because the symmetry is more complicated, there will be more indices. Okay, so instead of just one index here, you will have an object which has 3 indices. Okay, so then the other thing is, you can also, the one point about this covariant derivative is, imagine again you have a sphere, and then you take, so it's a 2-dimensional sphere, and you take derivatives of a vector. And the vector is like this. So then it makes a difference if we first take a derivative in this direction and then in that direction, or you first go in that direction and then in this direction. If you do that, the vector will point in 2 different directions. And the difference between these 2 directions depends on the curvature of your geometry. Okay? So then essentially there's a tensor which measures how curved your space is, and you just look at the commutator of 2 derivatives. So commutator of 2 derivatives is given by the curvature of the space, and so essentially, and this is this is quantified by the Riemann tensor. So Riemann was a famous mathematician in the 19th century, and that's why this tensor is called R. And just because this object has 3 indices, this Riemann tensor will have 4 indices. So, and so then essentially the statement is that this Christoffel symbol is related to this Riemann tensor just as A mu from our gauge theory is related to F mu. Okay? So it's exactly the same structure. Mathematically, it's just a different symmetry. Okay, so then this Riemann tensor tells you how much the difference between 2 vector derivatives on this curved space differs. And then you can do 2 things. You can define something called the Ricci tensor. And this is just a construction of 2 indices. Yeah, I'll be done in 30 seconds. Okay, so if you take 2 indices the same, there's a convention of summing over them. Okay, and then you can define something called the Ricci scalar. And this is just, again, you construct the 2 indices of this object, and this is R. And now I wiped it off, but earlier I wrote you this gravity action. So, and essentially I was starting with something in 10 dimensions. Then this is your Jacobi determinant, which makes your integral covariant. Okay, so that's the determinant of the metric. Okay, so then there's so-called metric spaces. And in metric spaces, the metric G mu enters this Christoffel symbol. Okay, so you can write this gamma in terms of this metric and its derivatives. And then R is exactly this R which I was talking about. Okay, so that's what I wrote on the blackboard 5 minutes ago. So that's the Ricci scalar which measures our curvature, and this thing is called the Einstein-Hilbert action, because from this you can write the Lagrange equation, and the Lagrange equation of this action is precisely the Einstein equations. So then, in Einstein, already put this cosmological constant here. So then I should say the Lagrange equations for this action are the Einstein equations. Okay, and I think that's all you need to know about general relativity to understand the rest of the 4 lectures. Okay. Of course, if you know already more, it's helpful, but if you never heard about general relativity, just think about this, and then this will be enough to understand the rest of the lectures. Okay, there's already red lights blinking there, so maybe I should stop. Thank you.
Okay, so let's thank Johanna for this excellent, fantastic lecture. And we resume at 4:40.